Let's look at solving one more recurrence relation. So let's suppose a sequence A0, A1, A2 is defined recursively as follows. So AK will be 2 times AK minus 1 for each integer k greater than or equal to 1. And my initial condition, A0, is A, where A is a constant. So it's some fixed number, you just don't know what it is. And I want you to use iteration to guess an explicit formula for this sequence. So remember how iteration works. You start with your initial condition. So my initial condition, A0, was A. And then we're going to use our recurrence relation to write down the remaining terms, successive terms. So A1 would be 2 times A0, or 2 times A. A2 would be 2 times A1, 2 times 2A1. So I'm just going to leave that as 2 squared A1, or sorry, 2 without an A1 there. Those should just be A's. A3, using our recurrence relation, it would be 2A2. So 2 times 2 squared A, so 2 cubed A. And then hopefully we can start to notice a pattern. A1, it was 2A, A2, it was 2 squared A, A3 was 2 cubed A. So if I had to guess, AN would be 2 to the n A. And there's my guess for the solution to this recurrence relation. So this kind of series is, again, a special type of series. It's known as a sequence. It's known as a geometric sequence. So here, I'm going to use R is a constant. And if you have a geometric sequence, it can be written as AK equals R A to the K minus 1. So in our previous example, R was 2. And if you have a geometric sequence, a solution to a recurrence relation for a geometric sequence, it would look like AN equals A0 times R to the n. Again, if you compare this to our specific example, R was 2 and A0 was A. If you plug those in, then you get the same formula that we got up here.